This episode is sponsored by Audible. The special theory of relativity tells us that one person's past may be another's future. When time is relative, paradoxes threaten. Today, we peer deeper into Einstein's theory to find that the immutable ordering of cause and effect emerges when we discover the causal geography of. Recently, we've been talking about the weirdness of space-time in the vicinity of a black hole's event horizon. Very soon we'll be dropping below that horizon to peer at the interior of the black hole. There, space and time switch roles. But to truly understand that bizarre statement, we need to think a little bit more about how the flow of time is described in relativity. Today, we're going to look at the amazing geometric structure that time, or more accurately causality, imprints on the fabric of space-time. First, let's recap a little bit of Einstein's special theory of relativity. There are two previous episodes in particular that will be useful here if you find you need more background. Special relativity tells us that our experience of both distance and time are, well, relative. If I accelerate my rocket ship to half the speed of light, the distance I need to travel to a neighboring star shrinks dramatically, from my point of view. An observer I leave behind, with an amazing telescope, observes me traveling the entire original distance, but will perceive my clock as having slowed. The combination of this length contraction and time dilation allows both moving and stationary observers to agree on how much older everyone looks at the end of the journey. Everyone agrees on the number of ticks that occurred on everyone else's clock. They just don't agree on the duration of all of those ticks. Reminder, time measured by a moving observer on their own clock is called proper time. But counting those clock ticks isn't the best way for everyone to agree on space-time relationships. There's this thing called the space-time interval that relates observer-dependent perspectives on the length and duration of any journey that all observers will agree on, even if they don't agree on the delta x and delta t of that journey. We've talked about it before, but it's a tricky concept to understand intuitively. But we want that intuition because more than proper time, the space-time interval defines the flow of causality. In relativity, 3D space and 1D time become a single 4D entity called space-time. To preserve our sanity, we represent this on a space-time diagram plotting time and only one dimension of space. We'll see our causal geometry emerge plain as day even in this simplified picture. There is no standing still on a space-time diagram. If I don't move through space, I still travel forward in time at a speed of exactly 1 second per second according to my proper time clock. Motion at a constant velocity appears as a sloped line, and the time axis is scaled so that the speed of light is a 45-degree line. Now, let's say we have a group of space-time travelers. They start at the origin where x and t equals 0. They race away to the left and the right for 5 seconds, according to their own watches. They all travel at different speeds, some close to the speed of light, but never faster. The path they cut through space-time is called their world line. My world line is only through time, and the tick marks on the time axis correspond to my own proper time clock ticks. The faster a traveler moves, the longer their world line. That's not just because of their speed though. To me, their clocks tick slow. They time their journey on these slow clocks, so I perceive them traveling for longer. Accounting for this, we find that our space-time travelers are arranged on a curve that looks like this. This shape is a hyperbola. Drawing a connecting line at the tick of every traveler's proper time clock gives us a set of nested hyperbolae. But these aren't just a pretty pattern. These curves are kind of the contours defining the gradient of causality, down which time flows, and etched into space-time by the equations of special relativity. But to understand why, we need to see how these proper time contours appear to other space-time travelers. Instead of doing that with equations, we can see it with geometry. First, we need to draw the space-time diagram from the perspective of one of the other travelers. To transform the diagram, we need to figure out what they see as their space and time axes. Time is easy. They see themselves as stationary, so their time axis is just their own constant velocity world line. And their x-axis? Well, from my stationary point of view, I define my x-axis as a long string of space-time events at different distances, but that all occur simultaneously at time t equals 0. To observe those points, I just wait around until their light has had time to reach me. At every future tick of my clock, a signal arrives from the left and the right, and I use that to build up a set of simultaneous events, defining my t equals 0 x-axis. Our traveller does the same thing, but from my point of view, their clock is slow, so I see them register signals at a different rate. At the same time, they're moving away from the signals coming from the left and towards the ones originating on the right, affecting which signals are seen at a given instant. The traveller infers a set of simultaneous events that to me are not simultaneous, but there is no preferred reference frame. Their sloped x-axis is right for them. Even just doing this graphically, we see that the traveller's x-axis is rotated by the same angle as their time axis. That comes from insisting that we all see the same speed of light, 45 degrees on the space-time diagram. Moving between these reference frames is now a simple matter of squaring up our traveller's axes. In fact, we grid up the diagram with a set of lines parallel to these new axes and square up everything, while maintaining our intersection points. My world line is now speeding off to the left, while our traveller is motionless. We just performed a Lorentz transformation, but using geometry rather than math. This transformation allows you to calculate how properties like distance, time, velocity, even mass and energy shift between reference frames. But check out what happens if I attach pens to all of the intersections when I transform between frames. They trace out our hyperbolae. Those intersections represent locations of space-time events relative to the origin. They will always land on the same hyperbola, no matter the observer's reference frame. I told you that these contours show where clocks moving from the origin reach the same proper time count. But more generally, each represents a single value for the space-time interval. The delta x and delta t of the event at the endpoint of a traveller's world line might change depending on who is watching, but the hyperbolic contour that they landed on, the space-time interval, will not. This is because the space-time interval itself comes directly from the Lorentz transformation, as the only measurement of space-time separation that is unchanging or invariant under that transformation. Now, we can finally get to why this thing is so important, and what it really represents. It may seem counterintuitive that an event very close to the origin, in both space and time, can be separated from that origin by the same space-time interval as an event that is very distant in both space and time. The hyperbolic shape seems to demand that. But remember, it takes the same amount of proper time to travel from the origin to a nearby near-future event compared to a distant far-future event on the same contour. From the point of view of a particle communicating some causal influence, those points are equivalent. The space-time interval tracks this causal proximity. We can think of these lines as contours on a sort of causal geography. The way I define the space-time interval, it becomes increasingly negative in the forward time direction. So we can represent this as a valley dropping away from me here at the origin. I naturally slide through time by the steepest path, straight down. I can change that path by expending energy to change my velocity, although doing so realigns the contours, so I always slide down the steepest path. There's no point anywhere downhill that I can't reach as long as I can get close enough to the speed of light. In fact, the nearest downhill contour defines the forward light cone for anyone, anywhere on the space-time diagram. But uphill is impossible as long as the cosmic speed limit is maintained. Breaking that speed limit and sliding uphill are equivalent. To reverse the direction of your changing space-time interval is to reverse the direction of causality. to travel backwards in time. The space-time diagram we looked at today was for a flat or Minkowski space, in which faster-than-light travel is the only way to flip your space-time interval. But in the crazy curved space within a black hole, it gets flipped for you. We'll soon see how this requirement of a forward causal evolution leads to some incredible predictions when we try to calculate the sub-event horizon interval of space-time. A big thank you to Audible for sponsoring today's episode, and also for making it possible for me to